So one final example of tying together the conservative vector fields with the fundamental theorem of line integrals. Suppose we have a vector field y squared over x squared I minus 2y over xj. And there's some sort of acting upon the object from 1, 1 to 4, negative 2. We're not even going to use the parameterization this time. We're just going to verify it's conservative. We're going to find the potential function. And then we're going to use the fundamental theorem of line integrals to find the work done. So this completely eliminates the f dot dr if it is indeed conservative. So first of all, let's define p and q. All right, so p is going to be x to the minus 2 y squared, just by using that old algebra trick that you just swing the denominator and make it a negative exponent. And q is going to be negative 2 x to the minus 1 y. We're just going to find each of the partials. The partial of p with respect to y is going to be 2x to the minus 2y. And then partial of q with respect to x is going to be positive 2, because the negative and the negative, x to the minus 2y. All right. And what that means is that, fortunately or unfortunately, depending upon how you look at it, this is a conservative function. Okay, students might not think it's a good thing because that means they have to go on to find the potential function for that conservative vector field. All right, teachers like to do that, like when it is conservative. So that means we can go forth and do more. So for letter B, now let's find the potential function. All right, so we're going to integrate, and we're going to integrate our good old function p, because as we've seen several times, p is really phi sub x. All right, so we're going to integrate x to the minus 2 y squared with respect to x, and that's going to help us to be able to find what phi is. All right, now in this case, we're going to add 1. We're going to divide by the new exponent, so that's negative x to the minus 1 y squared plus some function, which we're going to call g of y. All right, it's going to be a function of integration. Now, to figure out what gy is, we're going to find phi y. All right, that's going to be negative 2x to the minus 1y plus g prime of y. We're going to set that equal to whatever q is. All right, and it just so happens that q is the exact same thing except for the g prime of y. All right, and we see where this is going from the other few examples. All right. Notice that the left and right hand sides contain that negative 2x to the minus 1y, so that goes away. G prime of y is 0. That means that also g of y is 0. All right, and we like when that happens because that's less to work with. So our potential function, phi of xy, is going to be an easy one. It's just going to be this minus x to the minus 1y squared. All right, so that's all the way back here. Remember we said g prime or g of y was 0, so g of y just goes away. All right, so this is our potential function. Now that we know the potential function, it doesn't matter whether it's a curvilinear or whether it's a sinusoidal path, whatever it is, all we care about is going from 1, 1 to 4, negative 2. All right, so for item C, we want to go phi 4, comma, negative 2 minus phi 1, 1. All right, now a little bit more work this time, though not much. All right, so that's going to be opposite 4 minus 1 times negative 2 squared minus the opposite of 1 to the negative 1 times 1 squared. All right. If we compute this correctly, all right, I believe that this might work out to be 0, right, because we're going to end up with the opposite of 4 over 4, and then we're going to have plus 1, right, so this just turns into a positive. Our negative exponents is 1, and that means that there is no work going on here, all right, or no work necessary by either the particle or the force field. All right, so hopefully this gives you a good understanding of the relationships between potential functions, conservative vector fields, being able to find the work necessary to go through that vector field. In the next series of videos, we're going to be taking a look at a specific way to evaluate line integrals, called Green's theorem, and Green's theorem is going to be a special type of region.